Welcome to the 87th Theoretical Physics Colloquium by Marton Lajer, who's a postdoctoral fellow at Brookhaven National Lab. He received his PhD in 2020 at Edwards Lorand University in Budapest. He briefly was a junior research fellow at Wigner Research Center for Physics, and since early 2021, he is a postdoctoral fellow at Brookhaven National Lab, although because of the COVID, he still didn't physically move there. His research interests are in integrable models, sine codon model, 5 to the 4th, quarkyonic regime of QCD, and today he will be talking about when cold, dense quarks are not a Fermi liquid. And with that, I'll give the microphone to Marton.
Yes, thank you very much for the introduction and also the opportunity to talk here. Can you hear me well? As a first question.
Yes.
Okay, so today I would like to present the work in which I enjoyed the opportunity of working together with Robert Koenig, Rob Pisarski, and Alexei Zvelik, namely the strongly interacting matter in which in particular exotic phases it can behave as not a Fermi liquid as it will going to turn out. So when I talk about strongly interacting matter and about exotic phases, then I'm basically thinking about fundamental particles of strongly interacting matters, namely quarks and gluons, which constitute the familiar quantum field theory of quantum chromodynamics. Now, in the most simple case, then which is basically what we see around ourselves, is the vacuum of this theory, which is not constituted of the fundamental particles that appear in this action, but rather mesons, baryons, and stuff like that, which has the property of being singlets in the quantum number, what is called color. So QCD fundamentally consists of fermions, which are the quarks, gluons, which are bosons, and nothing else. And quarks have color, and also they have flavor. The flavor is what is basically corresponds to the usual names of quarks like U, D, N's, and so on. So as I said, in the vacuum phase of this theory, we actually don't see these particles lurking around, but rather they are arranged into bound states, which are confined together. So this is the usual picture of QCD. But actually, what we are going to be interested more in this talk is when there are extreme conditions in terms of temperature or in terms of the background density of matter, and it turns out that when in this extreme under these extreme circumstances, actually confinement can be lost, and also the spectrum can change radically in under those circumstances. So if you take these two parameters, temperature and the density of matter, then you can arrive at the phase diagram of QCD. And so the simplest phase I have been advertising is like here in the lower left corner, which actually corresponds to the QCD vacuum, and the mesons and baryons and stuff like that around. Now temperature is on the vertical axis, so if you start to increase the temperature, at some point you are going to lose this confined picture, and you are arriving at something that is called the quark-gluon plasma. I am not going to talk about the quark-gluon plasma, but instead the other axis on this phase diagram is actually the baryon density, and the phase I'm going to be most interested in is this intermediate phase, where we already don't have this original picture where like chiral effective theories work, but we are still not in the other asymptotic regime when the gauge coupling gets effectively small and we arrive at a color superconductor. So there is something in between that is referred to as generally as the quarkyonic phase, and most of the talk is going to be about this quarkyonic phase. So there are so this is a in general this is a very interesting and complicated phase diagram, and I will try to simplify it as much as is sufficient to talk about my topic. But in reality, this is a very rich field, and a lot of active research is being done trying to explore this phase diagram. And in fact, so it is actually it is actually a very hard topic to try to explore this phase diagram. But in broad terms, what we can probably say is that there are three main regimes in the low temperature regime of this phase diagram. One is nuclear matter, which is valid before the density gets comparable to the saturation density of usual atomic nuclei, and then in the other asymptotic regime, when the density is very large, then there is no confinement; it is screened, and instead, what you are going to have is a sort of an analogy to superconductors, when you get pairs of quarks that are confined together, and then basically the ground state of the superconductor is the condensate of this diquark bosons, and there is a gap in the spectrum due to the presence of this diquarks. But so these are the two opposite regimes, and then in the middle there is this most interesting regime of the quarkyonic phase that I'm going to talk more in the following slides. But basically the most important property is that in this phase the bulk free energy is that of quarks and gluons already, but there is a Fermi surface, and then the excitations around the Fermi surface are still confined particles like hadrons. Now, so the problem with exploring these phase diagrams is that QCD, and in particular NC = 3, is notoriously difficult to probe. So there are methods, there are non-perturbative methods like the lattice, but it turns out that the lattice works well for finite temperatures, but not so well for finite chemical potentials. There is a particular problem that is called the sign problem that prohibits going to the large chemical potential regime. There have been improvements. Actually, many improvements have been done at the Utrecht University, but still you can't really go by the lattice towards you can't go beyond the region when the quark chemical potential is about proportional to the temperature in some units. So the lattice is sort of ruled out, at least exactly for NC = 3. And of course, there is a hope that some point in the future, this can be probed directly by quantum computers, but that is far away in the future. So this is not available right now. And instead, what we can do is try to look at two limits and try to infer something interesting from these two particular limits. So one limit is when we take the number of colors from 3 to infinity, and then it turns out that in this infinite number of colors limit, there are analytic expansions available that go in terms of the inverse of the number of colors. And so this provides some way to get some analytic insights on what could happen. And the other the other limit of this region is NC = 2, where it's a bit surprisingly, it turns out that lattice can actually solve. So then the sign problem is not so prohibitive as in NC = 3. And so there are actually lattice simulations done for NC = 2 and in this high chemical potential, low temperature limit. And so what we can do is look at these two limits and try to infer what might be, try to interpolate between these two limits and try to infer something that might be relevant for NC = 3. So the plan of this talk is going to be the following. I'm going to talk about a bit more about quarkyonic matter and the fact that it gets anisotropic. And then what follows, I will try to introduce the concept of a Luttinger liquid that is relevant for anisotropic materials. And in the third part, then I will turn to a model of QCD in 2 dimensions, which is going to be relevant for this anisotropic description of quarkyonic matter. And then in the end, I'm going to present some insights of what this all can be relevant for neutron star cooling. So okay, so first let's try to motivate what is quarkyonic matter and how it comes into the picture. So most of the insights come from the large number of colors limit. So in the large number of colors limit, there is a wide range of the phase diagram when the temperature of deconfinement is almost a constant, as is depicted on this figure below. And then there is a particular chemical potential, or well, a range of chemical potentials that is well exemplified by this particular value of mu pairs, in which the deconfinement starts to go towards lower temperatures, and when you reach this color superconductor phase. And the way to well, say something about this this perturbation chemical potential scale is try to calculate the screening in this large number of colors limit, and this is indeed possible. So you can calculate the characteristic wavelength, or the inverse, which is the Debye mass of screening, that is the screening of the so-called electric gluons. Now this Debye mass has contributions at the one loop order from 2 parts. One part that comes from the gluons and is depending on the temperature, and one part that comes from the quarks, which depends on the chemical potential. And now we can argue that the onset of the perturbative regime, when the screening gets relevant at a fixed temperature, is when the red part, namely the part that corresponds to the quark contribution to the Debye mass, wins over the gluonic contribution. And then that happens at a particular value of the chemical potentials, which depends on the root of the number of colors involved. So there is a particular scale of deconfinement, and I will generally think that above this characteristic chemical potential mu pairs, we are in what is called the color superconductor regime, when there is no confinement. And below this chemical potential, but also bounded by another bound, namely the saturation density of, so the chemical potential corresponding to the saturation density of hadrons. So there is in between these two limits the quarkyonic phase, at least in this large NC limit. So the other point is that you can also look at the free energy or the pressure of quark matter, which again in the one loop order comes from 2 contributions, gluons and quarks, and you can also look for a balance between these 2 contributions, which is going to provide another limit, another threshold value for the chemical potential that comes now as the 1/4 power of the number of colors. And so at least in the limit when the number of colors is much larger than the number of flavors, there are actually 4 sections to which we can distribute, I mean, in a hand-waving manner, the QCD diagram, namely nuclear matter, 2 phases that are quarkyonic, in the sense that the bulk free energy is quarkic, but the excitations around the Fermi surface are hadrons. And then there is this perturbative regime when the chemical potential is asymptotically large and there is no confinement. But there are, so I would like to make a differentiation between these 2 quarkyonic regimes. So basically the argument is that for the relatively small values of the chemical potential, what we are going to see is that there is a pion condensation which has been known for a long time, and basically there are going to there can form also more complicated objects with inhomogeneous space-time, well, at least inhomogeneous space configurations that are called mesonic chirospirals. And in this other regime, there is going to be a similar but a bit different process that is going to go on and leads to strong anisotropy. And this region is what I will refer to as the region of quark chirospirals. So okay, so basically what I have said so far is very I mean, hand waving. So this part is really just a motivation for what is coming, and in fact there are in some way colliding or alternative explanations for what might happen precisely in this intermediate regime on the phase diagram. So in particular, there is one possibility that the transverse fluctuations can actually ruin this nice spiral structure, and in fact there could be a disorder phase of pions that could form, which is called a quantum pion liquid, and also there might be another thing to keep in mind that would be of relevance, is which is the so-called mode spectrum of bosonic excitations, which is predicted for a particular part of the QCD phase diagram, but well, novel research indicates that the region to which this mode spectrum could be relevant is actually much more extended than just the immediate vicinity of the critical point of QCD, and so these all could have an effect on this picture of what I'm trying to show, but as a first order in approximation, I believe that this is still deserves some interest, more so because the picture that I tried to draw so far relied on the large NC limit, but in fact there are also indications from NC equals 2 which predict an extended regime of this quarkyonic phase between the onset of the perturbative regime and the confinement, and between the hadronic regime. Now, of course, so this is to be taken with a grain of salt, because NC equals 2 is in a way very far away from NC equals 3, because then the baryons are bosons instead of fermions, and there is a Bose-Einstein condensate of them. But still, at least in some sense, we expect that certain properties of the quark matter should depend only very weakly on the number of colors, and at least this is a so there is some hint that instead this picture, that in fact this picture could be has something to do with reality, or could be worthwhile to examine. So now what happened? Sorry, okay, sure.
I think we have a question. Thomas, do you want to ask your question? Should I read it? Any even n is very different from any odd n. That's the question. Comment.
So yes, I mean, so for even n, baryons are going to be bosons. This is true. So yeah, so this is right. So yeah, so as
you understand some question here, the mass of pions here.
Yeah,
the mass of the pions here.
Yeah, so also the mass of the pions is not tuned. Yeah, exactly. Okay. You are right.
Oh, that's fine.
No, you are right, but we anticipate that this is not. So this is also a problem, but this is not such a big problem as the fact that there is a Bose-Einstein condensate. So okay, so the pion mass is large because the lattice simulations was done with the lattice regularization, and it was easier to work with larger pion masses. But yeah, so I mean, the pion mass, I think, could be made more realistic by working on a larger lattices and more numerical resources. And so you are right, this is an unphysical value of the pion mass, but so still, I mean, the real problem that comes here is because of the even number of colors that are here. Okay, but still, this is something that comes from a small number of colors and not something that comes from a large number of colors. Okay, yeah. So okay, so let's imagine that we are already in this quarkyonic phase, and first consider the part in which the chemical potential is between well, the onset of what would be the saturation density of nucleons and the onset of, well, and this intermediate value mu pi q that I talked about on the previous slide. So it's the first, the small chemical potential portion of the quarkyonic segment. Now, so what happens is that so there is going to be a Fermi liquid of fermions, but due to the large values of the chemical potentials, there are going to be the ground state is going to be unstable with respect to forming this interesting non-trivial, spatially non-trivial flavor structures that interpolate between different flavors, and so corresponding to these spirals, we can plot a dispersion relation of mesonic excitations, which is going to look like the figure which is in the left side of this plot. Namely, so that there are going to be what I call patch vectors that point in the direction of the spirals, where the spirals are going. So there are going to be a finite number of directions, and these are going to be superimposed atop each other. But the small energy excitations are going to be such that the dispersion relation of mesons appear on these so-called patches. So the patches are going to be the sections of the mesons in which they at the smallest energies they can exist. So as a general phenomenon, as the chemical potential increases, the number of patches is going to increase, and as the number of patches is going to increase, actually at least up to some point, the interaction between these chiral spirals of different patches can decrease. Sorry?
Nothing, it was just noise.
Okay. So yeah, so what is important is there are these patch vectors, there is a discrete number of them, and in the beginning, these are basically mesonic chiral spirals or mesonic density waves, and as long as the number of patches is small, then this is actually probably a relatively correct picture. But once the chemical potential is increased towards larger numbers, one can write down an effective theory of each density wave, and these effective theories of density waves are actually very anisotropic. So they are approximately one-dimensional Versumino-Witten models that are to which there are some transverse modes added to, and on top of that they are also interact with each other. But the point is that, so there are 2 points. So first, the transverse part of the interactions is going to be small when the effective size of the patches is small, and second, the interaction between non-coincidental patches can be small, at least as long as the angles between them are not becoming very small. But so there is a region in which we can think of this system as effectively a number of chains, one-dimensional chains or one-dimensional quantum field theories that are coupled together weakly, and if this coupling is indeed very weak, then we can actually think in terms of effective low-dimensional models and try to solve these effective one-dimensional models and try to infer something about them. So
I have a quick question.
Okay.
When you have so many of different pairs of these patches, wouldn't it essentially mean that the system becomes isotropic or almost isotropic? And in a way, it does mean that it's one-dimensional. It's just that weakly interacting model, but in 3 dimensions, 3 + 1 dimensions.
Yes, so I think eventually this is true, but let me just point out that first of all, the size of these patches is depending on the effective string tension. So this is so there can be a phase when the size of these patches is small, and second, so the effective propagator is yeah, so it's essentially a quartic. So basically, yes. So basically, you are right in that once these patches become essentially very close to each other, then eventually this anisotropy is going to vanish. As like just if you actually increase the chemical potential even further, then eventually you are going to get into this perturbative regime when there is color superconductivity. So I'm talking about a particular region for a certain number of patches, which is not too small, not too large, and in which the effective interaction can be actually weak.
Okay.
Yeah, so okay, so but even in this case, so when you have many small patches, you should take into account that on these small patches, at least when the temperature is very small, you can have effectively 2-dimensional modes excited, and therefore there is going to be a crossover temperature from the anisotropic but not one-dimensional regime that is indicated by this energy scale W to the really one-dimensional scale that is I will try to argue that can be a Luttinger liquid. And this actually leads us to what actually is a Luttinger liquid. So okay, so maybe it's best to start with the original description of what a normal Fermi liquid is. So in 3D, when you have an interacting system of electrons, and in the simplest possible case, when there is no symmetry breaking, what happens is that you can imagine that the Fermi surface of the electrons is somehow adiabatically connected to the free gas of electrons. And if this picture is indeed right, then what turns out is that the Fermi gas picture of free electrons gets approximately true, and many of the notations that we learn from the free gas of fermions in a finite chemical potential just carry through simply to the interacting Fermi gas, even when the interaction strength is actually large. So this is indicated in if I try to draw the occupation number of electrons as a function of the wave number, then just like in a case of free electron gas, which would be just a Bose distribution, I get something similar, which is well modified because of the presence of interactions between the fermions, but still there is a very well-defined Fermi surface that can be seen as one depicts the expectation value of the occupation number. And so in the simplest case, if the small energy excitations can be thought of as being particle Hall pairs, and the excitation spectrum of these particle Hall pairs are going to be this nice continuum, and the quasi-particles that appear atop this Fermi surface are going to be very much like the non-interacting Fermi gas, with the difference that now these quasi-particles are going to have a finite lifetime in general, but in fact, this lifetime has a singularity atop the Fermi surface. So when you excite quasi-particles around the Fermi surface, first of all, they are going to be fermions, and second of all, their Green function is going to have poles, and third, when you are in the vicinity of the Fermi surface, then the lifetime of these quasi-particles are going to be long. And also, as another equivalent description, you can say that the spectral function at the Fermi surface has a Dirac delta peak, and the Green function has conventional poles. So this is the usual situation that happens in 3D. This can be hampered when there is also spontaneous symmetric breaking involved, because then you can have a gap. But in general, this is still true that you are going to have some sort of Fermi surface, gapped excitations, but the excitations are going to have poles in their Green's function. Now, in contrast, when you are not in 3D, but in 1+1 dimensions, the situation is kinematically very different, because then instead of a nice, well, the particle Hall excitations can still be a continuum, but now you are going to have these cusps in the particle Hall excitation spectrum, which has eventually a very solid effect on the Green functions. So now what happens is that this nice Fermi surface or Fermi sphere that you start with in 3D now reduced to, well, the Fermi sphere itself is reduced to a line, and the Fermi surface gets reduced to just 2 points. And so the low energy excitations are going to be around those points. So what you can do is either you take a fermion starting from the vicinity of the Fermi point and excite it, making a hole to around the other side of this Fermi point, or you can excite it to the other half of the Fermi surface. And naturally, this means that there are going to be two kinds of fermions involved, one that goes to the right and one that goes to the left, and they have linear dispersion. So now this is in the absence of interactions. But when you turn on the interactions, which means you have some 4 fermion interactions between these one-dimensional fermions, something very interesting is going to happen. So first of all, at low energies, the relevant interactions that can happen is quite limited, also for kinematic reasons. So particles can scatter either forward or backward, or, well, at least in condensed matter, there is also a sort of unclapped scattering where the momentum of quasi-particles are only conserved up to reciprocal vectors. But in general, all these low energy processes can be identified with 4 coupling constants, which I now imagine to be the dimensionless versions of coupling constants, G1 to G4. And what is very important about these Luttinger liquids is that these 4 fermion interactions that are schematically depicted with these Feynman diagrams actually translate to bosonic quadratic expressions. Because in 1D, there is a very special property that you can do on fermionic systems, namely, you can bosonize them. So in 1+1D, I mean. So in 1+1D, you can make actually an operator identification between the massless Dirac fermion and the massless compactified boson. And so as a result, you can express the fermionic Hamiltonian that describes one-dimensional fermions interacting with each other as a bosonic theory, which only involves quadratic expressions in a single boson, which, well, if you neglect the spin degree of freedom, is just going to be a theory consisting of a single bosonic field, and that you can solve by a Bogolyubov transformation. As a result of this Bogolyubov transformation is going to be that your bosonic Lagrangian is going to attain 2 non-trivial parameters into itself. So there is going to be a parameter k, which is called the Luttinger parameter, and there is going to be another parameter v that is going to be the effective speed of the low energy excitations. Now, and these two parameters are going to depend on the original coupling constants of the fermion interactions. So there is a dictionary from fermion-fermion interactions to these Luttinger parameters and the effective Fermi velocity. And so this is a, so this is a compactified boson actually. So this is why this normalization k can matter and can be simply transformed out. So so there is this nice bosonic description, and what is important is that once these parameters k and v get non-trivial values, then the correlation functions of the original fermions actually going to be modified such that instead of the usual poles, now they are going to have cuts. So they are, in a way, they are going to get incoherent, and that means that essentially their lifetime is going to be proportional to their energy. So they are not going to be well-defined quasi-particles around the Fermi surface anymore. But really, the true excitations in this interacting phase that describe the one-dimensional theory is going to be this collective bosonic excitations. So with this picture in mind, now let's look at QCD and what happens to it in 2 dimensions. So as advertised already, in 2D you have bosonization, and in fact this was considered a long time ago, or more than 40 years ago. People try to write down the QCD Hamiltonian and write it into a bosonic representation. And they were actually sort of successful in this. At least they, even in the simplest context, when you just use what is called the Abelian bosonization, so you associate bosonic fields to each contributor or each part of the fermionic field separately, and you try to see what's going to happen. What you are going to get is a complicated bosonic Hamiltonian, but at least when the number of flavors is 1 and the number of colors is arbitrary, you are going to get a relatively nice Hamiltonian that you can write in 2 lines. What I would like to highlight here is that so there is what seems to be a low energy part, which contains of kinetic energies of the bosons, some cosine terms, and also there is something that looks like a high energy part, which is proportional. So which in particular there is a part which is quadratic in the fields, but is proportional to the QCD coupling. So this is the QCD coupling. So one may ask the question, what happens when this coupling is strong, but we are looking at low energy excitations? And then, so since this is essentially mass parabola, this is actually a multidimensional mass parabola, we can look at the 0 modes of this mass parabola and just neglect the massive fluctuations. So we can rearrange the fields such that we keep those fields that correspond to the 0 modes of this mass parabola, and then look at the effective Hamiltonian that results from this. This is one possibility. And the other possibility, which works well for more than 1 flavors, is to use Witten's non-abelian bosonization, in which you can translate a number of fermions residing in some representation of the unitary groups SUNC and SUNF to a sum of Versumino-Witten models and the U1 boson. And so when there is no mass term of the quarks, then basically what you get is really just a Versumino-Witten model, well, a sum of these 2 Versumino-Witten models. And you can do the same analysis trying to look at the low energy and strong coupling limit of this non-abelian bosonized Versumino-Witten model. And what you are going to get is again a nice form of the effective potential, which consists of some U1 boson, a Versumino-Witten model, and also a perturbation. So this is a in general, it's a non-trivial, non-integrable perturbation that opens a mass gap. Now, so this is a low energy effective Hamiltonian. And actually, what is interesting is that you can think of this as a version of the Skirma model, which is here can be in a way derived from the QCD Lagrangian, because you can apply the bosonization formulae to that. So once you have the bosonic version of the QCD in 2D, you can now look at what happens at a finite value of the chemical potential, namely when you introduce a U1 chemical potential, so a baryon number chemical potential. And this can be easily translated to a shift of the field that is coordinate dependent. And you can look at what happens to this theory. Now, the simplest, okay, so once this coordinate dependent addition is added, then the effective Lagrangian is going to be modified in a way that you are going to see the appearance of these Luttinger parameters, one for the U1 part, and actually there are corresponding Luttinger parameters for the SU1 part, but I'm going to focus on the U1 Luttinger parameters now. And this effective theory that is valid for finite values of the chemical potentials is in a way very simple, and the coherent excitations suggest gapless bosons. And so the argument is that at finite chemical potential, since this is what describes QCD in this large chemical potential, well, relatively large chemical potential limit, this is what can be relevant also in this quarkyonic 2 regime of QCD. Now, so I'm a bit running out of time, so I will try to be quick. But so the main line of argument is that when you fix the number of flavors to 1, there is a special property of integrability that makes it possible to actually solve the low energy part of QCD in 2 dimensions in a much more precise way, and that actually makes you able to calculate these Luttinger parameters explicitly, so non-perturbatively, exactly. And in order to see how this happens, it goes by introducing some notation from integrability. So the most important property of integrable systems is that there exist higher spin conserved charges, but since we are in 2 dimensions, this doesn't mean that the theory has to be trivial, because in 1 + 1D, the Coleman-Mandula theorem can be avoided. But still, there are very strong constraints on the possible scattering processes, and in particular, the scattering has to be completely factorized. And since it has to be completely factorized and purely elastic, then if you know the scattering, the elastic scattering phase in 2x2 scattering, then you basically know everything of the scattering in the theory. So what I'm going to be concerned about is the S matrix, which is just a finite part of really the S matrix element between 2 particle states that can be parameterized in terms of Mandelstam variables. But since it's elastic and it's 1 + 1D, there is actually only one Mandelstam variable that remains relevant, and this can be chosen to be the Mandelstam S. And if you plot this 2x2 S matrix as a complex function of this Mandelstam variable S, you are going to find on the complex plane, in the general case, a multiplicity of cuts in the general non-integrable case. But this is going to be simplified by just a single pair of cuts in the integrable case, because there is no inelastic processes at all. There is only the 2x2 elastic process. So there is just one pair of cuts, and therefore this is a much simpler analytic structure. And due to this much simpler analytic structure, it makes sense to transform away both of these cuts. And this is why we introduced the rapidity parametrization, because in the rapidity parametrization, you have a completely analytic function, well, meromorphic function, because there are still poles, but otherwise a completely analytic function of this S matrix space. And so due to this analytic property, you can write down functional equations that come from the factorization of scattering and also unitarity and crossing. And by the solution of this functional equations, you can write down the exact S matrix for the Sine-Gordon model. Now this is known for a long time, but what you can do at our case of special interest is that so first of all we are going to be at integer number of colors. We are going to be and we are going to prove actually special points of this Sine-Gordon model where the scattering has the other special property of being completely diagonal. So there is no non-trivial soliton anti-soliton scattering. So scattering is completely diagonal here. And also we can write down the spectrum explicitly, so we know the mass ratios in this model explicitly. There is the soliton. There are breeders which are composites of solitons and antisolitons with particular masses, and basically that is all, at least from u equals 1. Now what you can do in the presence of the chemical potential is a very nice thing, but basically because there is only elastic processes, then what you can do is to think in terms of a first quantized viewpoint when you imagine that your system is is confined to a finite volume, and then you have a multi-particle state in a quantum mechanical sense when you have some wave function, and due to the boundary conditions of the finite volume, these wave functions has to be periodic with respect to each coordinate of each particle. And so you can actually write down a quantization condition taking into account that the interactions between these particles are local. So in a way, it's like you have a delta gas, just like now the interaction of this delta gas is going to depend on the momentum of the particle. So it's going to be rapidity dependent, but still you can write down a system of equations which arises from getting through a particular particle on all the other particles. And this yields, taking the logarithm of this quantization condition, yields the so-called beta-Young equations. This provides the quantization of momenta for these particles, and by this it also provides the energy of the multi-particle states, because you can think of the energy as just the sum of the one particle energies. After you have this nice picture in this discretized way, when you have a finite number of particles, you can take a continuum limit when you essentially, instead of a finite number of particles, you have a condensation, so to speak, of the solitons, which are going to constitute a Fermi sea, and you can look at what happens to the energy in the ground state in the presence of this Fermi sea. So what you can do is to write down the continuum version of these beta-Young equations and solve them as integral equations. The integral equations is completely well known. It's exact. You can write down it exactly. The kernel is going to be an analytic function of the rapidity. You can solve, and then you are going to get an exact expression of the ground state energy. Actually, you can do the same thing for the charge of this ground state, by introducing an extra particle to this condensate, you can also obtain exactly what happens to the one particle excitation energies. So you can ask the question, what happens if you have a condensate with Fermi points in rapidity space equal to B, and add an extra soliton, or add an extra anti-soliton, or add an extra breeder, and you can solve these equations for the energy, the quasi-energies of these particles by solving these integral equations, and then you are going to find the dispersion relations of each of the breeders, and also what happens to the energy in the presence of an extra soliton. And from this, in particular, from the behavior of the epsilon s, so the result of adding an extra soliton, is going to let you predict the value of the effective velocity of the Luttinger liquid, and by the effective charge of adding an extra soliton in the presence of the Fermi surface is going to let you predict also the Luttinger parameter. Now, so once we have our hands on these integral equations, we can also solve a question of what happens to the mass gap of like the breeders that are involved. So they are going to be massive particles, and as you increase the chemical potential from the onset of the Fermi surface, then you are going to see that each of these breeders are going to get larger in mass, which is a good thing, because the lowest mass scale of the breeders is actually an extra UV limit of this Luttinger description. So the Luttinger liquid effective theory is going to be valid as long as its energy scale is smaller than any of these massive particles, namely these breeders. But these get heavier as the chemical potential gets larger. So as anticipated from these integrability related quantities, the effective charge that was related to the extra charge of adding one soliton to the Fermi surface in 1D, and also the slope of this one soliton dispersion relation, you can infer exactly what these Luttinger liquid parameters are. So at least in one flavor, two-dimensional QCD for an arbitrary number of colors, these parameters can be actually obtained in an exact fashion, at least to the extent that this low energy strong coupling approximation of QCD is valid. Now for NF larger than 1, we don't have integrability at our disposal, unfortunately. So then even the low energy theory is not going to be just a single sign Gordon, but it's going to be a Vesumino perturbed by a trace of the Vesumino field. But still, you can consider some quantity perturbatively which contains the quantities of interest. And namely, we chosen the dynamic U1 susceptibility, which is basically the 2-point function of the U1, the time-like component of the U1 current. And so even though what we get by a perturbative expansion is a coupling in fact in the fermion mass, the explicit fermion mass that is put into the Lagrangian, but still since we are solving for the full omega and q dependence, we can still from the analytic structure of this dynamic susceptibility, we can infer separately the value of the Luttinger parameter and the speed, and at least to the leading order in a particular coupling constant, which is related to the chemical potential, we can actually solve for the Luttinger parameter and the speed for an arbitrary number of flavors. But here in these pictures, I actually decided to depict NF equals 1 in order to show how they compare to the exact results that come from the solution of the thermodynamical beta ansatz. And it turns out that at least for NF equals 1, the leading contribution of that can be solved perturbatively is already a very in a very good agreement with the exactly obtained value of the same quantities. So at least in NF equals 1, it turns out that this perturbative analysis provides a very good estimate. And now, of course, it is a question what happens to NF larger than 1, but at least it's a good sign that this has something to do with the actual Luttinger parameters. And what this all is good for is that since we have an effective Luttinger liquid picture, which is very simple, the U1 part is just a free boson and the other part is a Bell-Zumino, we can actually try and write down the 2-point correlators of the nucleons or the delta fields, or at least what corresponds in quantum numbers to those fields in two-dimensional QCD. And there are, because these effective theories are so simple, we have these simple expressions for the 2-point correlators of the nucleons, which are going to involve exactly these Luttinger parameters that are highlighted in red and blue that I just calculated in the previous slides. So by this analysis, at least in this effective two-dimensional theory, you can get information on 2-point functions of like baryons. And they are actually, if you look at the exponents, you are going to see this non-standard power law behavior of the coordinate dependence of these correlators. So the picture that emerges is that there are the bosonic excitations that are the elementary excitations of the bosonization, and there are also fermions, but these fermions are incoherent in the sense that their 2-point functions are going to have these non-trivial cuts. And these correlators can be actually calculated, and also the Luttinger parameters that these correlators depend on can also be calculated. And yeah, so in general, what we can say is that there are, yeah, so there is also a color sector that I didn't really talk about so far, but there is a large gap in which the high energy excitations of like the blue balls come in. This is the part that was neglected in the bosonization of the Lagrangian. And when I talk that there is this quadratic part of the bosonized gauge interaction, and I only look at the zero modes, I basically neglected this color sector, which contains high energy gapped excitations, and these are all neglected here. But still there are no free quarks, because even in the color sector you are going to see bosonic excitations. At least the elementary excitations are going to be bosons corresponding to blue balls, but these are going to have a very large mass. Okay, and so I'm basically pretty much running out of time, but maybe some last comments is that first some recap. So we have nuclear matter, then two different phases for quarkyonic matter, and then asymptotically there is a perturbative regime. So if I turn this around and I try to think in terms of where this might be actually relevant, I might look up to the sky and try to look for some compact stellar objects in which these extreme densities can be reached. So now, first of all, there is an estimate of this perturbation mu, which is around 1 GeV. So we are really looking at chemical potentials that are smaller than this 1 GeV. So now, if I write the same content into a different arrangement, I might look at what is an interior of a neutron star that is a compact stellar object. And if I move from inside out, from the regimes of relatively small density towards regimes of larger density, the very schematic sketch that then I can write is that basically there is going to be a crust which is composed of the usual atomic nuclei, but then there is going to be a large region of nuclear matter where very interesting things can happen, but I basically just consider it as one large sector. And then there are these quarkyonic sectors, and perhaps even there is some sort of color superconducting in the core. And of course, I don't know anything about how these look like in terms of real space arrangements. So what are the thickness of these regions in terms of kilometers? But at least one may think that some of this picture could be relevant. Now, so how this might be relevant is that you can write down an effective model of neutrino emission. And it turns out that in the presence of these Bell-Zumino-Witten fields, there is an enhanced neutrino emission due to a virtual process when a Vesumino field can virtually decay into a nucleon pair, and then by a big process they can emit neutrinos. So there has been work on this problem, but what I would like to highlight is that the dependence of the free energy on the time, which is essentially can be translated to, which is a proxy for the dependence of the temperature over time, depends on, well, the electrochemical potential, the running strong coupling, but also temperature. But there is also the specific heat of the material that emits these neutrinos, and the temperature dependence of this specific heat is going to be different in a very low energy phase when the transverse fluctuations are also interesting, and this intermediate temperature regime when as I told, this Luttinger liquid might dominate. And what this can do is that this can actually change the prefactor in the time dependence of the temperature of the neutron star. So there are some direct there could be some direct consequences, although of course, I mean, you have to measure the temperature dependence of a neutron star, but at least in principle there are some practical consequences. So, but this could be actually very relevant from other transport properties, because I think that probably the most important thing is that the 2-point functions are going to be qualitatively different from that of a Fermi liquid. And so since the neutron stars may reach quarkyonic densities, this can be relevant for them. And okay, and so of course there are a lot of work to do, because I mean the relation to neutron stars and in fact whether this quarkyonic phase really emerges in real QCD is an open question. But it would be really interesting if something like this would actually happen. Okay, so with this rush, I thank you for your attention.
Thank you, Martin, for a nice presentation. We will have now some time for questions. So if you have a question, please raise your hand in the reactions and you'll be able to ask it. Any questions from the audience?
Okay, two questions, your statement. First slide here, the main point is here, show it here, this one here, there's no idea, right?
Sorry?
Look, there's a new idea here. This one comes down here. The main point is, right? This one here. The center of point number 3. There's no idea.
So, yes. So okay. So yes. Okay. Okay. So this one.
Okay. Make sure.
Yeah. And
okay.
Yeah.
My second point from the history. Can you slide of 1.7? In history, when old arm is here.
1.7 or
yeah.
Which one? This one maybe or
no
or 17.
No, 1.7.
17, I suppose.
This one.
Here. Oh, here. It's a history. I know him in Slack here, when he's graduate student, him. He was wonderful. He put much impact on the interest. However, he was a postdoc in Slack when I met him many times before. He couldn't find faculty position, right? Is that's correct? He never find a faculty position here. For him, nobody share. It's very good to share it. What impact from him? Had one impact as a graduate student, as a postdoc. Why not find a faculty position, right? Okay.
Well, is that a question or a statement, though?
No. Is that true? I wondered what happened to Ballooning, because that paper is very clever. He uses this clever gauge. It's really pretty, and it just he sank from sight.
Yeah. Thank you. Well,
okay.
Life is not fair.
Life is not fair.
Let's get more positive. And do you have any other questions to the topic that we had today? I actually had a simple question before somebody else will think of something else. On page 34, you were showing the spectrum, and there was something that really brought my attention. The dashed line that is going to 0, suggesting that there will be a gapless excitation developing when you're approaching mu equal ms. Is that the correct?
Oh, yes, exactly. So this is actually when the chemical potential is gets equal to the soliton mass. Yeah.
So what's the nature of that?
The dashed line is when, okay, so here there is no Fermi surface. Or so, well, but you would call a Fermi. So there is no condensation of the solitons. Yeah. And from here on, okay, so what happens is that, so this is actually the soliton, the effective soliton mass, as the chemical potential is increased. And yes, it becomes 0. And after it becomes 0, I actually used the zeros of the one particle energy of the soliton in order to obtain the extent of this fermion condensation in rapidity space. So this B is essentially, this is related to the Fermi points, as I don't. So this is actually I think so. This is related to the cosine hyper, because this is rapidity. Sorry, this is the cos minus 1 of kf. Right. So this is the rapidity space Fermi point, and once yes, as you point out, so once you are in the presence of negative values of this one soliton effective energy, then you can look at when this actually gets 0, and this is going to point you out as a function of the chemical potential, which is an external parameter. And so by solving this equation self-consistently, you can actually figure out what is the extent of the Fermi surface.
Okay, I see.
So yeah, so this is important that this gets 0. Yes.
So essentially, you're saying this is when the Fermi surface develops.
Exactly.
The gap excitation develops.
Exactly.
Okay, that's fair. I understand now. Any other questions? I have some more, but I don't want to occupy all the time. So yes, Renat, please.
Hi, thanks for the very nice talk. So since you were working in 1 + 1 dimensions, so there is this phenomenon of spin charge fractionalization sometimes. The electron, for example, can separate in 1 + 1 dimensional electron can separate into a spin-on and the holon that's carrying the charge. Is there something similar happening here as well?
Oh, so yes. So in the simplest case, but you get in the low energy description is just one. I mean, it's just at least okay. So at least the U1 sector is just one component boson. So I wouldn't say that.
Okay.
Yeah. So essentially, this is more to do with spinless fermions in this case.
Yeah.
So is this like a holon then?
It's hard to say for the fractionalization, right? You need both the charge and the spin degree of freedom.
If you're considering color as a charge here, I assume the excitations are colorless.
Yes.
They carry U1 charge and flavor.
Yes. So
obviously a fractionalization.
Alexei, can you please repeat why it's obviously fractionalization? I'm not sure we caught it.
You look at this effective action. There is field phi and there is matrix field G. Matrix field G is a matrix in flavor space. So all G and phi enter into expressions for the baryon operators. And the correlation functions for the baryon operators have this complicated Paolo form in which parts which come from U1 sector and parts coming from the SUNF F sector are fractionalized.
Yes. So when the number of flavors is one,
it's a complete
analogy. So then okay.
Standard Luttinger liquid with columns and spinons.
Okay. Rena, you're happy with that?
Yeah, of course. Thanks a lot.
Yeah. Okay.
Yeah.
Okay, good. Any other questions? Any other questions? I was actually wondering about, I know it's only sort of speculation, but nevertheless, since you brought it up, about the application to the neutron stars. So essentially, my understanding is that you are saying, since you have this non-Fermi liquid behavior, you may have actually maybe the other slide where there was the comment about the entropy, right? So essentially, the specific heat will be behaving very differently, linear instead of quadratic. So my understanding is you are saying that the cooling will be enhanced by that. Is that the statement?
Yes. I mean, yeah, of course. Yes. So
at small temperatures, basically T is much larger than T squared. So it seems like an enhancement to me.
Yes.
The follow-up then is there are other speculations about all kinds of enhancements of the cooling by the properties close to the Fermi surfaces that develop due to, for example, superconductivity as well. Is this? Are you aware if this is any comparable to that enhancement, or this is very different qualitatively? Any sort of thoughts about that?
Okay, so since this is essentially dependent on the logarithm, then the exponent of the specific heat is just going to change the prefactor of the cooling. So yes, so in fact this might be a bit hard to measure, because we are really trying to get something about the prefactor of the same time dependence. But yes, at least one can say something like this. And yeah, so in
go ahead. Sorry.
So in the superconducting phase, I mean, so there is a gap in any case in the superconducting phase, and so I don't know. Maybe Rob has something to comment on.
Yeah, actually, I was going to comment. Yeah, in either the nuclear phase, where you have nucleon superfluidity or superconductivity, or the deconfined phase, where you have color superconductivity, you typically have a gap. And the experimental evidence, as far as I can understand from conversations with Jim Latimer and others, is still confused. But it seems like you need more cooling. And actually, our mechanism is very similar to when you have pion condensation. And you have a coherent excitation that can decay through basically the same diagram. It's just here it's related to a Weston-Witt model. So yes, the point is you can get enhanced cooling, and you seem to need enhanced cooling. But there's so much data now, and it's changing very quickly.
Well, cooling is a very complicated for neutron stars, even without all of this. So of course it's probably not so going to be easy to approach even this really measurements. But just to understand the predictions of this model concerning the cooling, at least that was my question. Thanks.
Yeah, the basic thing is you'll have an effective theory where everything near the Fermi surface is massless, where nothing's gapped, and it'll be controlled by these excitations. So you could at least write down some sort of effective theory to describe this, and then compare it to hopefully observations in the near future.
Sounds good. Any other questions before we will start wrapping this up? I don't see any questions right away, so let me use this moment to thank Martin again for a nice presentation, for taking time to present these ideas in a clear and relatively concise form. And I really appreciate that. So thank you on behalf of everybody.
Yeah, I thank you very much.